Welcome to the 24th lecture of surface engineering. We already have started discussing the specific techniques for various approaches of surface engineering of engineering solids, and we began discussing the techniques which are concerned with applying controlled amount of surface deformation onto the surface, principally with an aim to create residual compressive stress to improve the fatigue resistance or certain other kinds of resistance against surface failures. The principal mechanism of that approach was to create strain, plastic strain, and increase dislocation density onto the surface so that eventually we create residual compressive stress. Today we are going to discuss surface hardening, which is a thermally activated process with the same aim that we want to harden the surface, and we are essentially, when we talk of surface hardening, in particular we are talking about all the discussions are concerned with steel, the interstitial solid solution of carbon in alpha iron. So, in steel, we all are aware, if you look into the first view graph, if you just consider the solid state part of the iron carbon diagram. So, this is the so called eutectoid portion. So, in this surface hardening approach, we are concerned with a composition range which is somewhat in this range. So, somewhere around, let us say typically about 0.3 to about 0.8 or maybe even less amount of carbon. So, this is the level of carbon content, and we are talking about primarily plain carbon steel, but this is certainly applicable to alloy steel as well. But we require typically somewhere around 0.3, I would say optimally 0.4 and above. 0.4 weight percent of carbon or above. This is what we need. Now, why we need this carbon content, I will come to that in a minute. But the most important thing that we need to realize is that we essentially, in this kind of a treatment, if we are talking about a component, the cross section of which is, let us say, of this diameter, we would like to harden the surface only up to a certain depth from the surface and not through and through. So, the core will be left in ferritic state. The surface, because of transient heating, is supposed to, so essentially the surface should experience a heating cycle, which is, so this is temperature and this is time. So, we want the surface to reach fairly high temperature, and the so called high temperature, what we mean, should be somewhere around here. So, if this is AC3, the ferrite to austenite transition line, we would expect a temperature typically which should be AC3 plus about 50 degrees centigrade. So, this is the austenitizing range. So, depending upon the carbon content, whether it is 0.6 or 0.4 or 0.3, we just find out what is the corresponding temperature at the AC line, and then add up around 50 degree or slightly more to take care of the possible thermal fluctuations during the heating process. So, the temperature here is somewhere in that range, AC3 plus 50 to 100 degrees centigrade, and then subsequently we cool. We actually cool by way of some accelerated cooling, by way of quenching, which could be by application of certain fluids. We will also discuss that in a minute. So, the whole idea is to use steel whose composition is between this range, and then subject it to transient heating to a temperature which is in the single phase austenitic zone, and then subsequently we quench using some kind of a quenchant to bring it to room temperature. And in the process, we expect the surface zone up to a certain depth to undergo a phase transition from austenite to martensite. So, the strengthening is because of martensite, as compared to the previous surface deformation induced processes like shot pinning or shock pinning or laser shock pinning, where we introduced plastic strain and dislocation density, and that's how we created residual compressive stress. Here, the process involves a solid state phase transformation wherein austenite transforms to martensite. So, as I said, this is primarily a thermal treatment. We want a hard surface and a soft core, because the core, for example, this ferrite here, will actually be able to absorb energy, including impact or high strain rate energy, whereas the surface will be able to resist deformation due to wear, abrasion, erosion, or any other kinds of surface damages. So, it's important that we actually create a graded microstructure. What we mean is that if this is the cross section, we want the gradation such that we have very fine acicular ferrite onto the acicular martensite onto the surface, and then in the core we can afford to have polyhedral ferritic or ferritopearlitic microstructure. So, in the process we actually see a gradation from pure martensitic to martensite plus pearlite, and then eventually ferrite pearlite combination. So, this is obtained or achieved through a thermal activation by way of one of the two. We are going to discuss so-called flame hardening and induction hardening. So, the heating is done either by flame or by electromagnetic induction, and in the process the hard surface that we create is called case, and typically the case depth could be a millimeter or less, even a few millimeters in some cases. So, here is a real-time picture. So, this is a very large gear which is subjected to flame from multiple sides, and this assembly is rotating at a particular speed, so that the surface by turn, the entire surface by turn is exposed to high temperature, and this is the kind of heating cycle the surface actually experiences. So, we heat, we actually allow certain residence time, but this is transient heating. So, obviously, this is very short time, and then subsequently we quench using some kind of a quenchant. So, first let us pick up the flame hardening, where we actually use, it could be simply an oxyacetylene or some other form of flame. So, we use a burner. So, this is a typical burner with several orifices. So, we actually can, so this top portion is primarily to throw the oxygen and acetylene combination, and by combustion of these gas mixture we get very high temperature at the tip. The tip typically takes up the ellipsoidal form, and then subsequently from the sides of the burner nozzle we also have orifices or openings through which we can throw water. So, when this flame is off and the stock or the surface of the stock has reached the required temperature, then we want immediate quenching, and that is obtained by throwing water or various kinds of coolants, mixture of water and salt, or maybe water and some kind of polymers and so on, or oil, and then that fluid flow basically extracts heat from the surface and causes very fast quenching of the surface. So, one thing what we must remember is, if you recall, I kind of just now showed that we are only talking about the solid state part of the phase diagram. We are not referring to the portion which actually is related to the peritectic. So, this is the liquidus line. We never cross the liquidus line. So, we are well within the single phase austenitic zone. So, there is no melting. The typical hardening temperatures would be about 730 to 7065 degrees centigrade. This essentially depends upon if this is AC3, and depending upon the composition that you are talking about, it can be on the higher side. For about 0.3% carbon, you actually go to a temperature which is close to 1000 or a little over 1000 degrees centigrade. But if the composition is 0.6 or close to eutectoid temperature, eutectoid point, then you're talking about 727 plus about 50 degree. So something like 700 and anywhere between 730 to 780 or that kind of a temperature range. So typically the temperature that we generate onto the surface, now this is what we are talking about, the temperature of the stocks, but the flame temperature certainly would be a little higher because you are actually heating up through radiation from the flame. So the temperature at the surface will be determined by the flame temperature, the size and shape of the flame, the speed at which the workpiece is moving, either rotating or translating away from the flame, and of course the material properties, which means the conductivity, the density, the specific heat, melting temperatures, and so on and so forth. The heating time should be sufficient for thermal and compositional homogenization. Now, we are talking about, let's say, 0.4% carbon steel. So if we are talking about 0.4% carbon, at room temperature, we expect a 0.4% carbon steel, typically a mild steel, should have a microstructure which will be both perlite and some amount of ferrite. So we'll have perlitic zone and maybe some ferritic regions left in between. So typically we expect sort of 50% perlite and 50% ferrite. This is the kind of microstructural aggregate that we expect from a 0.4% carbon steel at room temperature. So when an aggregate with both ferrite and perlite is subjected to rapid heating to a temperature above the AC3, so we expect this aggregate to turn into single phase austenite or gamma. That takes time because you have to dissolve Fe3C. So you have alternate sequence of Fe3C and alpha, and this Fe3C has a composition of 6.67% carbon. On the other hand, ferrite composition is somewhere here, which is typically let's say 0.0258% of carbon. So you have to swing, you have to allow compositional homogenization within a very short distance though. So typically this is about a micron or a micrometer or a few micrometer apart. So 6.67, 6.67 and in between 0.025. So within about, let's say, 2 or 3 micrometer. So whatever is the heating temperature, you must also allow sufficient time for, first of all, thermal homogenization, which is faster because the thermal conductivity is always higher than the diffusion coefficient. But you also should have sufficient time given so that compositionally the whole region, when it converts to gamma, this gamma should have a uniform composition of 0.4% carbon throughout. So compositional homogenization is also important. These are the various kinds of the gas mixtures that we use. So if you use a combination of oxygen air with oxygen or air with acetylene or natural gas or propane, so this is the kind of flame temperatures that you can develop. So if it's oxygen, so this is the range of temperatures you can generate, or with air the temperature range would be slightly lower. So one has to control the flow of gases at the tip of the flame so that the right kind of temperature mix is maintained. So when you heat, so this is how the flame, which is typically assumes the shape like this, and this is going to heat up the surface. So let's say this is the heated zone, and if you now take a section, if you take a section like this, and on this section you see the isothermal contours. So for example, these are in Fahrenheit, so approximately the temperatures would be kind of little over half of this. So the temperature at the surface, or the meniscus at the surface, this is where you have the maximum heat and the temperature will be the highest. As you go down, you obviously the heat has to flow, and that is primarily determined by the conductivity K, and this is how the temperature flows into the interior. but the isotemperature contours, meaning this is the line throughout which will be maintaining the same temperature, or this is the trajectory of the same temperature points. Now, why is it semicircular? It's because heating right below is maximum, and similarly heat flows not only in the perpendicular direction or right below, but it also propagates laterally. So because of heat propagation in all directions, at least into the vertically downward as well as laterally to x and y directions, the contour surface temperature contour is going to be semicircular like this. And as we go to lower and lower, higher and higher depth below the surface, the temperature decreases gradually. So if you and this temperature also, there is a transient heating. So with time, this isothermal contours change. So this is what you expect at 0.1 millisecond region, but after 1 second, that means 100 times more than that, if the heating continues for 100 times more than that, so 0.1 millisecond becomes 1 second, then the temperature, which earlier was about 1000 Fahrenheit or maybe 550 or so degrees centigrade, has now reached easily 1650 and so on. So this is only limited to a very shallow depth. So the surface actually should not be exposed to very high temperature, but on the other hand, the temperature at the surface should be high enough so that up to the desired depth, you actually expose the material to the minimum possible temperature or minimum desirable temperature, which should be above the eutectoid temperature. But of course, there will be a region which is called the heat affected zone. So this region, so let's say this is the boundary unto which you are able to heat to a temperature above AC3. So are you into the single phase gamma region, you are able to convert everything into gamma. But there will be also a region below which will be experiencing a temperature which will be between in the two phase region of ferrite plus gamma. So this is single phase gamma. And there will be also a region which will actually remain as ferrite plus pearlite. So if this is the composition, from the surface, a portion below the surface will go into single phase gamma, a portion below that will be ferrite plus austenite, and then finally you'll also have a certain depth which will be only remain as ferrite pearlite combination. This portion which is gamma, pure gamma, or the portion which is partly ferrite and partly austenite, these two austenitic regions or these two regions having austenite will directly convert into martensite. So we are going to see fully martensitic and ferrite plus martensite combination. So this is typically the configuration, for example, for a shaft with a circular section. So you are heating it from all sides, and the heating ring actually can move up or down, vertically up or down, and as a result you start, let's say, heating from here, and then you go all the way down to, so you're able to actually heat treat the whole surface. The important point is that heating temperature should not cross the fusion temperature or the so-called solidus temperature, so that some liquid forms. We don't want that should happen at all. So heating should be confined below the solidus temperature, and heat flows through thermal conduction, and once the temperature has reached the required level, then we also are able to throw water through other orifices and immediately quench the material, quench the surface to room temperature. So the cycle will be room temperature to austenitizing temperature, and then subsequently quenching back to room temperature. So this is the typically the temperature band that we actually target. So this is the eutectoid point, and we are talking about typically steel of this composition range. So this is the level of, this is the kind of temperature that we heat up to. But since it's a transient heating, very difficult to maintain precise temperature, and it is not going to be isothermal condition. There will be a gradation of temperature from the surface to the bottom or to the interior. So, as I already said, that we expose to high temperature, whereby we have single phase austenite, and then we quench, and in the process we expect the surface to create, at the very surface region, we expect very high hardness, over 60 Rockwell hardness scale, Rockwell C hardness scale, and the typical case depth, the hardened depth, can be anything from about 0.7 or 0.5 to as high as 6 millimeters. So, we are talking about more than, a substantial amount of depth from the surface. So, typical applications, the components which are amenable to such surface hardening by flame would be the lathe beds, the centers, the crankshafts, the piston rods, gears and sprockets, teeth of the gear, axles, cams, shear blades, and so on and so forth. These are all steel products, and this whole process is applicable primarily to steel, and as I said, which should have minimum of 0.3, 0.4% carbon content. Okay. Now, so these are the various geometries which actually can be subjected to a shear blade or a gear teeth, or again another gear teeth, cams, and various kinds of shafts or screws and nuts and so on, where the surface always should have higher hardness and higher wear resistance. But the core we would purposely leave as ferritic or ferritoperlitic, so that it can absorb energy and of mechanical deformation and provide toughness. So, the important considerations are the head design, the flame configuration, the nozzle quench nozzle configuration, and the velocity with which we throw the coolant and so on. So, we basically can have three types of heads. One is a rectangular head. So, for materials which are rectangular in nature, maybe a blade or a shear blade like that, or a cutting tip, so which are rectangular or square or thin sheets and so on. So, we use a rectangular head for heating. We can use a toroidal head, which basically is applicable to cylindrical or circular parts like rolls and races, or we can use a contoured head. So, for example, we have a typical, we have a very complex shape of a component like this. So, for treating such a surface or a component, we would like to also have a nozzle which actually will mimic the shape of this kind of a component, so that the distance from the tip of the nozzle to the surface is maintained constant. So, these are the design aspects of various nozzles that we use for heating. We actually can have all these heating devices should also have an system of should integrate with a quenching system. The coolant usually is water, or it can be water with some mixtures of maybe polymers or salt or something, or it can be even oil if it's usually if we are employing hardened steel alloy steel, then we don't need very drastic quenching. So, instead of water, we can use in that case oil. After the process is over, that means after the flame hardening is over, we actually may need a follow-up tempering process, because a material which is through and through hardened and having, let's say, predominantly maybe 90% martensite or so, the remaining portion of course is likely to be retained austenite, or in some cases maybe pearlite. But if you have more than 90% martensite, the surface will be extremely hard and also brittle, and because of this combination you cannot machine them, and there will be certain amount of distortion which may happen subsequently. So, in order to make the surface amenable to subsequent machining or shaping or some other treatment, we may like to also follow up with a tempering process, which is a reheating process. So essentially, we can use the same flame to heat to a temperature way below the eutectoid transition point. So that means now when we talked about so this is temperature and this is carbon content. So when we are talking about tempering, so for flame hardening, we aimed a temperature zone somewhere here for a composition like this. But if we want tempering to follow the hardening process, then we would go somewhere around 500 or not even 500, somewhere around let's say 250 to 350, at the most 400 degrees centigrade or so. So this would be the typical zone. Okay. And what is important is that why are we doing all these exercises? Because we want to harden the surface, and by way of bringing in martensite. So we want a predominantly martensitic surface. The ultimate aim is to see a hardness level which is typically about 60 in the Rockwell C scale. Now this is possible no matter how efficiently we do. Whether we are able to do it efficiently or not, this is typically possible for the composition range, which is 0.4% carbon and above. So this is the carbon content, the homogeneous carbon content of the steel. So if you have a steel which is less than 0.4% carbon steel, even if you conduct the process very efficiently, you may not be able to reach the requisite hardness. So the hardness level could be as low as 40 Rc. So this is no good. So the important guideline here is that we want this range of composition to be subjected to flame hardening and not this range, because a requisite amount of carbon is necessary in the stock during heating process in order to get the desired level of hardness. If you recall, during the discourse on martensitic transformation, I did mention that one of the biggest reason of seeing martensite as the hardest solid solution phase is because of the fact that martensite actually is derives its strength from primarily from supersaturation. So it is essentially a supersaturated solid solution, and the supersaturation, if it is due to less than 0.3% carbon, then that is not sufficient for creating the desired hardness after martensite formation. Now, there is another method which is equally important, and in fact, instead of flame, here the thermal activation or so-called the heating effect is given by electromagnetic induction. So just like flame, what we have here, say for example, this is a typical shaft or a rod which we want. So this is the cross section, and we want the surface up to a certain depth to get hardened, and the core should remain perlitic or ferritic, but the surface should be martensitic. So with that intention, we simply have a toroidal coil, electromagnetic induction coil, through which this rod can be inserted, and we apply very high frequency current so that electromagnetic fluxes are created, and the fluxes intersect the surface, and in the process through eddy heating they create heating onto the surface. So the temperature again, so we exactly see a temperature time profile which will be like this, and then will be subsequently quenched by either dropping into a quenchant or at some other arrangement by throwing compressed air and so on. So we need water cooled copper coil for magnetic induction. We need to reach the required transformation temperature, and this temperature is reached because of the alternating current that we send to the coil. So when we send alternating current to the coil, we create alternating magnetic field, and this magnetic field interacts, the fluxes interact with the surface and create certain thermal state, and that takes the stock to a temperature above the austenite formation range. So we can control more precisely here the exact depth of heating. The core remains unaffected, but the surface goes to temperature above austenitizing, and then subsequently we quench in oil or maybe some other media. So this is exactly the arrangement that I was talking about, and we actually, what we must realize is that this induction hardening follows exactly the Faraday's law, and which means that if we apply alternating current reversing at a very high frequency, let's say 60 hertz or so, then this is going to lead to generation of very high eddy current. So the heating will be through this eddy current. Also, in addition, there could be alternating cycles of magnetization, demagnetization. So there will be a hysteresis, and the area under the loop will also lead to hysteresis heating. We can, as I mentioned, we can control the depth very precisely, and this depth of heating will primarily depend upon the parameters, the heating parameters, the time of heating, the current, the frequency, so that we reach the correct austenitizing temperature, and then subsequently we quench by either spray or by dipping or dropping into a liquid bath. So this is the depth. This is the circular section. So so this is the coil current, and this coil induces current into the stock circular section of which you are seeing here. So particularly the eddy current that we generate actually is responsible for heating, and this is the overall picture of electromagnetic induction. So these are the fluxes which are created from these induction coils, and so the coils are perpendicular to the stock, and this is how the flux is generated, the left hand thumb rule, and then these fluxes intersect the surface, and if the material is magnetic, then actually we get even better heat or faster heating, and that's very true for materials, ferromagnetic materials like steel. What is important is for us to know that why I was mentioning that we can control the depth more precisely. The depth is an inverse function of the square root of the frequency of induction. So accordingly, by applying the frequency, we actually can heat up to a temperature above the Curie temperature, but subsequently when it's quenched, it undergoes the Martin-Stich transformation. But the degree to which we heat will primarily depend upon the range of frequency that we apply for inducing current. For electromagnetic induction, if the frequency is less than 10 kilohertz, then this is the relationship that we follow, or if the frequency applied is higher, say for example from few hundred kilohertz to even megahertz, then we apply the second relationship. But what is important is the depth from the surface, that for example if this is a stock, then this is the depth from either side that we are subjecting to. So this depth can be very precisely controlled by way of controlling this frequency of induction. And typically the depth can be anything from less than a millimeter to a few millimeters. So this is the relationship I was referring to, and it is because of this the depth is inversely proportional to the frequency square of the frequency, and this is what essentially leads to what is typically referred to in the literature as skin effect. So you actually can harden or heat the surface to above the eutectoid and the austenitizing temperature by way of controlling the frequency. So the frequency of current reversal is an important factor, and the depth will depend upon the resistivity of the material, the magnetic permeability, the frequency of as I said, the frequency. So what is also important is that the copper coil, which is generally used, water cooled copper coil, which is generally used for induction, the number of turns, the distance from the workpiece, and of course the power and frequency, all these are important process parameters. Time is also very important, because the residence time at high temperature determines to what extent from the surface you are able to penetrate the temperature. And we already saw that no matter whether it's flame or induction, we do generate such isothermal contours from the surface as heating profiles, and this changes with time because this is transient heating. So what is important is that we not only maintain the external parameters like frequency and the current and so on, we also apply such induction effect for a limited time, for a controlled time, so that the maximum temperature that we reach remains within the solid state and doesn't go into the liquid state. All right. So these are various applications, many industrial applications for various manufacturing processes, various household appliances, then medical appliances and so on. And this is the microstructure that we target at the surface. So predominantly martensitic. When I say predominantly, I don't mean 100%, but anywhere typically 80 to 90% of martensite onto the surface. And the remaining portion, of course, will be the retained austenite. So this is typically a configuration wherein you are seeing that these are the induction coil and this is the shaft which is being fed into it, or if it's a gear teeth, this is, so you actually will have a configuration which is going to be, so this is the rotating part and you'll have various number of such teeth of the gear like this. And so if you are targeting one of these teeth like this, then the coil should be properly designed. The geometry of the coil should be so designed that it actually can fit in exactly to this. So now you are in a position to harden only the surface of the teeth to the desired depth. There's one last thing I wanted to mention is that the heating so far we have done is either by flame or by induction. There's another way of doing this, and this has very limited application but is nevertheless quite effective, is when you use an electrolyte. So you actually are using an aqueous bath, electrolytic bath, wherein by applying DC pulse, not AC, and controlling the current and the composition of the electrolyte, you actually can create a hydrogen film onto the surface, and because of the resistance created by this hydrogen film, you can do heating onto the surface. So it's the correct electrolyte that you need to select, and during off time the electrolyte extracts heat from the solid stock, and that's how you can actually allow heating and cooling cycle, and as a result of which you can do hardening. So you can take it to austenitic state and then subsequently convert this to martensite onto the surface. So this is the biggest utility of electrolytic surface heating is related to the fact that if you have a bath and if you have a stock here inside the electrolytic bath, then you can do heating uniformly, or you can harden the entire stock in one shot uniformly, which is not going to be possible when you are using a nozzle for heating or an induction coil for hardening the surface. You cannot do for the entire length together. But here in electrolytic heating, you can do that for the entire stock because whole thing is immersed in the electrolyte. So it's now time to recapitulate what all we have discussed. So we talked about flame hardening and induction hardening, and by now we should be able to understand what's the difference, subtle difference between them. The underlying technique is heating and cooling. Of course, after heating there has to be quenching. So that's the common thing. The most important thing is that in both the cases we expect the stock to have sufficient carbon, so typically over 0.3, 0.4% carbon, and then it goes to austenite and subsequently get quenched so that we get martensite, and hence that's how we create a hardened surface. So it is essentially a solid state hardening process through martensitic transformation, and we require steel which can be plain carbon steel but with at least 0.4% carbon, or maybe alloy steel with sufficient amount of hardenability of it. Of course, between the two, induction hardening is more precise because of the so-called skin effect we just heard, which is the depth of heating being inversely proportional to the square of the frequency of alteration alternation of current. And last thing we talked about was the electrolytic heating. And what is important is that you are able to use or heat and convert the surface up to the limited depth uniformly throughout the surface, no matter what the shape and geometry of the solid component is. So I think that's all for the time being. Thank you very much.